For the last 20 years, surface dressings have been employed only for the maintenance of secondary roads carrying light traffic, and this technique has not advanced at the same rate as other highway techniques. Hot mixes, on the other hand, have developed considerably. In some cases, the accumulation of layer upon layer has led to a reduction of headroom under bridges and in tunnels. In other cases, to the footpath being at a lower level than the pavement. Yet surface dressing is the technique most suited to preventive maintenance in the form of a thin layer. On a smooth pavement, the sand patch depth test gives a large stain. After the application of a dressing which restores the surface roughness, the same test gives a small stain. The rougher the surface, the smaller the stain. The surface dressing seals the pavement and limits aquaplaning because of its draining structure. It contributes to driving safety by improving braking conditions when the pavement is wet. But the surface dressing must not be used merely to cover up underlying defects. An acceptable underlay is the primary condition for final quality. If the underlay is too deformed, the riding quality must be improved before the dressing is applied. Patching is performed, or levelling with gravel emulsion. Potholes must also be filled in, avoiding patching which causes localized bleeding. The contractor can choose between several types of dressings depending on local conditions and traffic. Incorporating traditional binders and good quality aggregates, the conventional type of dressing is suitable for roads carrying light or moderate traffic. If the traffic is heavier and faster, it is preferable to use an improved dressing incorporating viscous binders, sometimes with polymers added, and clean, well-shaped aggregates of high mechanical strength. For surfacing individual points, bends and accident black spots, it is advisable to choose a high-performance dressing whose constituents are very carefully prepared. Synthetic resin binders and aggregates of exceptional quality. Applying a surface dressing means making a series of choices, guided by Section 26 of the Standard Specifications and by the Surface Dressing Directive. Let us see how these different choices are made in the case of a project of average importance. The first link in the chain is the binder, which makes the pavement impervious and binds the aggregate to the underlay. The consistency of the binder first affects the wetting of the aggregate, which, if it is to be perfectly satisfactory, requires a certain degree of fluidity. It next affects the behavior of the freshly laid dressing under traffic, hence the importance of the choice of viscosity, itself influenced by the intensity of traffic and the time of year the work is performed. If the binder is too fluid, tangential stresses due to traffic cause it to rock. If it is too viscous, the aggregate is insufficiently moist and there are substantial losses. Next comes the choice of the aggregate. The characteristics required of it are considerable because the aggregate is under direct attack from traffic and from atmospheric agents. The service life and the anti-skid properties of the dressing largely depend on the mechanical properties and the geometry of the aggregate. The geometry is defined by three dimensions: length, coarseness, and thickness. The coarseness is rated by screening through square meshes. The thickness is rated by screening through slits. The coefficient of flattening is then defined as the percentage of elements in a batch in which the ratio of these two magnitudes is at least 1.58. Another aspect of the geometry of the aggregate is its angularity. The number of rounded faces must be minimal. Besides being determinant where macro-rugosity is concerned, the geometric characteristics influence the theoretical batching and rejects. The need for a tight particle size envelope and low tolerance is explained by the fact that a very wide particle size envelope leads to unsatisfactory laying of the aggregate and hence to waste. Waste can also result from a difference in covering power. It can clearly be seen that a given volume of aggregate of the same coarseness but of different length does not cover the same surface. The mechanical properties of the aggregate are measured in the laboratory by means of different tests which reproduce the dynamic effect of vehicle tires. The fragmentation of the aggregate under repeated impacts is stimulated by the Los Angeles test or by the dynamic fragmentation test. The micro-Duval test in the presence of water gives the resistance to frictional wear on the macroscopic scale, that is to say, the length of life of the edges. Frictional wear on the microscopic scale is determined by running a tire in the presence of water and an abrasive. The evolution of the smoothness of the aggregate is expressed by the accelerated polishing coefficient. This generalized bleeding corresponds to a series of inadequate characteristics. A difference in wear also occurs, as is clearly seen. Wear is a minimum when the mechanical characteristics of the aggregate are satisfactory, and is very considerable when these same characteristics are inadequate. When the road has to carry more than 6,000 vehicles a day, the aggregate must be rejected if the micro-Duval test in the presence of water gives a value greater than 15, or if the accelerated polishing coefficient is less than 0.4, or if the Los Angeles test gives a value greater than 25. Beyond these eliminatory values, a certain compensation between the different characteristics occurs. For example, if the aggregate has a satisfactory coefficient of flattening with a Los Angeles value equal to or less than 15, and if the micro-Duval test gives a value equal to or less than 5, then an accelerated polishing coefficient equal to or greater than 0.4 can be accepted. If the micro-Duval test gives a value of 15 or less, then the accelerated polishing coefficient must be equal to or greater than 0.5. Often, the adhesion between the binder and the aggregate is consolidated by the action of a dope. Mediocre affinity leads to failure. Laboratory tests reveal the importance of this problem from three aspects: overall adhesion, passive adhesion, and active adhesion. It is then possible to define remedies if need be. Overall adhesion, assessed by the Vialit plate test using dry unwashed aggregates, reveals, among other things, the effects of dust present on the material. If adhesion is poor, the aggregate may have to be washed or dedusted, and the test is then repeated to see how effective this treatment has been. If the result is satisfactory, the passive adhesion is checked by the static immersion test, which makes it possible to evaluate the risk of the materials being stripped by water. If the adhesion is poor, the bond between binder and aggregate must be strengthened. The dope to be used is selected by treating the binder in the mass, and the efficacy is checked. If the result is satisfactory, two cases may occur. The aggregates in situ are dry and the bonding is acceptable, The aggregates in situ are moist, in which case the active adhesion is assessed by the Vialet plate test performed in a moist atmosphere on moist, unwashed aggregates. If adhesion is poor, doping by a locally suitable technique may be envisaged. Doping in the mass of the binder, interface doping, pre-mixing or pre-treatment of the materials. The efficacy of the treatment is then checked. If the result is satisfactory, the bonding or the combination of binder, aggregate and treatment is accepted. But what structure is to be adopted? This will be decided by the speed, intensity and weight of the traffic and the state of the underlay. The one-course structure consists of a layer of binder and a layer of aggregate. This does not give the best drainage, especially when the aggregates form too tight a mosaic, but its roughness is satisfactory. The two-course structure consists of a layer of binder, a layer of aggregates, another layer of binder, and then a layer of smaller aggregates. Particle sizes may be continuous or discontinuous. A variant is to spread two successive layers of chips, generally of discontinuous particle size, on a single layer of binder, more strongly batched than in the one-course structure. This type of one-course structure, called double chipping, is a happy compromise between the other two structures. It gives roughness, drainability and durability, together with a firm hold on the aggregates, avoiding the danger of broken windscreens. The particle size of the materials influences the macro-rugosity of the dressing. It is also involved in several respects in the phenomenon of the embedding of the aggregate in the underlay, giving an impression of bleeding. There may be actual bleeding if there is an excess of binder. If the binder is insufficiently batched, plucking occurs. The batching of the aggregates is also important. For example, in double chipping, the first layer must reveal 1/3 of black, so that the chips in the second layer place themselves and give solidity to the mosaic. In all cases, an excess of aggregates means an immediate and considerable displacement, with obvious inconvenience to road users. Let us now take a look at how the work is performed by a qualified personnel. Proper organization is the first requirement. Stocks of aggregates must be constituted and served by functional equipment on areas that have been cleared and laid out so as to allow of optimal rotation of trucks.
Bon, après la 2 chevaux grise, tu peux y aller, hein? Libère la circulation. À toi.
Adequate road signs and protection also have to be provided to facilitate the work itself and the circulation of traffic. Previous sweeping must not be forgotten. It is essential. The size of the working site and the formulations adopted determine the choice of the spreading equipment. On this site, corresponding to average conditions, the binder is sprayed under a pressure of 4 to 6 bars by a spray bar fitted with cone nozzles, each of them theoretically delivering a constant quantity of binder. Two other types of spray bars are also used. One is the Leroux or Eure-et-Loire spray bar, which delivers the binder in thin jets under a low pressure of about 0.25 bars. Spray bars with flat blade nozzles are usually fitted to spreaders in which the pump is slaved to the speed of the vehicle. These nozzles deliver a flat, solid, triangular jet of binder. It is obvious that any defect in the functioning of the equipment, block nozzle or spray bar wrongly adjusted for height, upsets the transverse and longitudinal distribution of the binder. It is therefore essential to check that the equipment is working properly. Spraying may be controlled in two ways. The first is very simple in design and use. It consists of placing metal rulers on the pavement containing receptacles which are weighed before and after spreading. From this we deduce a curve of transverse and longitudinal distribution of the binder. The second method, still under experiment, involves marking the binder with indium 113M, which emits gamma rays. The radioactive tracer is automatically extracted and introduced into the bitumen, and its distribution is checked. After the binder has been spread, testing is performed by moving a collimated detector along a rail at a constant speed. The numerical data are recorded at predetermined intervals of time, and from them we deduce transverse and longitudinal distribution for several positions of the rail. The proper functioning of the different components of the sprayer must also be checked. Here we see the test bench on which binder batching components are verified at the road equipment test station in Blois. Pumps and filters are checked here. Between the sprayer and the chip spreader, interface doping is performed to protect the dressing from rain. A chip spreader of the conventional type is used. The angle of the dumper determines the rate at which the chips are spread. They may be distributed by gravity, by vibration, or by rolling. The distribution system ensures their batching and allows of partial spreading if necessary. Improvements have been made to this item of equipment. The width of chip spreading may be adapted to the width of binder spraying. The rotation of the distributor roller is slaved to the speed of the vehicle, and the chips are spread from a low height to avoid uncontrolled bouncing. This improves transverse and longitudinal distribution. The mosaic is immediately formed by a compactor fitted with smooth pneumatic tires, inflated to a pressure of 5 bars and loaded to at least 1.5 tons per wheel. Ordinary traffic, necessarily driving slowly, completes the process. To limit the effects of rejection, sweeping must be performed as soon as possible. Immediately, if the nature and viscosity of the binder make it feasible, and in any case within 24 hours of the laying of the dressing. The use of aspirators like this one is likely to develop considerably on roads carrying heavy traffic. They avoid numerous accidents and make it easy to recover the material. The success of a surface dressing depends on a series of choices and predictions. The choice of constituents, the nature and viscosity of the binder, the geometric and mechanical characteristics of the aggregate, and the dope. The choice of formulation, that is to say the choice of structure, of particle size and proportions. The choice of suitable equipment in proper working order, which means that it must have been checked. The planning and organization of the working site. Trained personnel headed by a supervisor who can make decisions to set matters to rights if any untoward incident occurs. If any one of these conditions is not satisfied, the risk is considerable. If 2 of them are unsatisfied, trouble is probable. If 3 of them are unsatisfied, then failure is certain. Awareness of these facts and progress achieved at all stages of the work have given surface dressings a new lease of life. They are indeed beginning to be used on main highways and motorways. Technically advantageous because of its thinness and its exceptional anti-skid properties, and at the same time economically feasible, the modern version of the surface dressing may be considered as a rational and systematic method of maintenance.